Hello. I think the screen sharing needs to be enabled.
Yes. Hello. Thank you for joining. All right, try now.
All right. Can you all see that?
Yeah, looks good to me.
Okay. Yeah. So I'm ready to start whenever you guys are. If you want to kick things off, or do you prefer to wait a little bit until more folks show up?
No, I think this is good. I think we have a good group enough, and people will probably continue to trickle in as we go on, so I'll just let them in. So let's start. So thank you, Sergey, for making the time to join us. For everyone else, Sergey will be talking about data-driven reinforcement learning in robotics, language, and beyond. And in particular, this has lots of relevance to much of the stuff we discuss and work on here at Carper. So super excited for the talk, and please take it away, Sergey.
Great. Thank you for the intro. So I'll talk about first some higher level things, and then I'll actually zoom in on a few different applications. This is not a super technical talk, but I will have some pointers, for those of you that want more of the technical points. So to start us off, let's start with like a kind of a big picture question. For large scale machine learning, what is it that really makes kind of current machine learning methods work? Well, there's a lot of like new technical ideas that have come up over the last 5-10 years. But time and time again, it seems like the following themes seem to permeate all the most successful results. The use of large high capacity models trained on lots of GPUs with, where they spend lots of cash on, and large data sets. And traditionally, these have been large labeled data sets. So certainly the big successes in computer vision starting about 10 years ago have really been driven by high quality labeled data. But more and more, increasingly, the big successes are coming from unsupervised training or self-supervised training, followed by a more modest amount of label training. So, classically, these results are driven by large labeled data sets, but more and more we want to be able to leverage giant unlabeled, easy to get data sets like data scraped from the web. And that's kind of the, what self-supervised or unsupervised learning is supposed to do. But when it comes to unsupervised pre-training, like language modeling or contrastive pre-training, a reasonable question we could ask is that, well, if these methods encode some kind of knowledge about the world into the model, where does that knowledge actually come from? Like, what is the model learning when it's trained on lots of text or lots of images? Well, classically, unsupervised learning is learning P of X. It's learning about the data distribution. And that's, for example, what large language models do. And if you imagine that you got your data by scraping the web, what you're really learning about is the behavior of whoever collected the data on the web. And there's something actually a little bit uncomfortable about this, because if the whole point is to grab lots and lots of freely available kind of garbage data that's just lying around unused, and yet at the same time, it really matters how the data was collected, because that's essentially what you're learning. These two things seem a little antithetical. So basically, for unsupervised learning, the data distribution actually really matters. But the ethos behind unsupervised pre-training is that you shouldn't care about the data distribution, just you throw everything in the kitchen sink into the bucket. So there's a little bit of a tension there. And as an aside, like maybe that's why prompting large language models is a little bit of an art, because without doing anything particularly careful to like fine-tune them with nice instructions, it's almost like you have to reverse engineer the thought processes of people who wrote stuff on the internet to figure out what you can write that'll get completed in the desirable way. And similarly for image generation models, it's like, while the ethos is that you could just grab all the data and get your hands on, in reality, all the very best image generation models are trained on somewhat carefully curated data sets. Again, kind of somewhat antithetical to this idea. So if we want to think about a better way to leverage large and somewhat uncurated data sets, we could step back a bit and maybe ask an even more basic question. Why do we need machine learning in the first place? And to be really reductionist about it, we can step back even further and say, why do we need a brain? So we can ask this guy, Daniel Walpert. He's a neuroscientist in the UK who works on brains. He knows a lot about brains. And he has this to say: we have a brain for one reason and one reason only, and that's to produce adaptable and complex movements. Movement is the only way we have of affecting the world around us. I believe that to understand movement is to understand the whole brain. Now, it won't surprise you to know that Daniel Wolpert works on the neuroscience of motor control, but he has a point, because insofar as our thinking influences the world, it influences the world through our movements. So we could formulate a postulate inspired by this for machine learning. We need machine learning for one reason and one reason only, and that's to produce adaptable and complex decisions. Our brains influence the world through our movements. Our machine learning systems influence the world through the decisions they make. And in some cases, the decisions are obvious. It's like, well, if you're controlling a robot, the decisions are how to move the joints. If you're controlling a car, the decision is how to steer the car. But if you have an image classifier or a text generation system or something, that thing is also making decisions. You know, for an image classifier, maybe the image label is the decision, or maybe it's what happens afterwards. So if you tag users in a photo, you're really making a decision about how to interact with that user, which might affect them in various ways. Maybe if you tag them in the photo and you get the wrong person, maybe they'll stop using your website, right? So there's consequences to these decisions, and that's important to consider. So if we kind of embrace this perspective that all machine learning systems really are about making decisions, maybe we could say, well, can reinforcement learning, the mathematical formalism we use to study decision making, give us a hint for how to approach these large scale training problems? So maybe this large, cheap data set of previously collected data, combined with this limited amount of supervision, can work in the following way. Maybe the prior data tells us how the world works. It doesn't tell us what we should do. It doesn't tell us what are good decisions. It just tells us what's possible. And then the limited amount of supervision we receive maybe tells us what the task is, so that we can figure out what are the good decisions to make. And that now makes a lot more sense, because now we're not saying we're going to copy everything in this uncurated garbage data set. It's more that we're going to look through it to understand what could be possible in the world, and then among those things decide on what is the best choice. So you could imagine that you have a big data set from all the past interactions and tasks that you've done. And when you get a new task, you're going to reflect on all that past experience and figure out the best possible model for addressing this new task. So in principle, at some very high level, reinforcement learning gives us a way to think about doing this. In practice, of course, it's not that simple. It's not that simple because reinforcement learning is really two different things. First, it's a framework for learning-based decision-making. So it allows us to go from predicting labels using ground truth data to predicting actions to achieve desired outcomes in a temporal process. But reinforcement learning is also another thing. It's an active online learning framework for control. So if you open up a textbook on reinforcement learning, you'll typically see a diagram like this, a loop where the agent interacts with the world, and through that interaction, iteratively gets better and better. That's very appealing because it's very naturalistic. We think this is how humans and animals learn, this kind of loop. But it's very clunky in the real world, because if you want to train, let's say, a language model on billions of documents of text, are you really going to have billions of interaction steps every time you retrain your model? That's just never going to work. So basically, almost all real world learning problems look like decision-making problems, either in disguise or not. But also almost all real world problems make this online thing really clunky. So we would really like the left thing without the right thing. So can we make RL look more like data-driven learning? Can we essentially get away from this very on-policy, rigid regime? And the answer is yes, we can. And that's what the study of offline RL is concerned with. Offline RL is basically RL applied to static data sets. Take a static data set, maybe lots of logs of dialogues or lots of data of an autonomous car driving, whatever you have, and squeeze out the best policy you can from that. And then once you've done that, you can fine-tune that policy more with online interaction. But the point is to get as much of that generalization juice as you can out of the offline training. So that's kind of the concept. And in today's talk, I'm going to talk about the fundamentals behind offline RL methods. I won't go into a lot of detail about algorithms, but I'll sort of give you a little bit of a picture for what these methods are supposed to do and roughly how they do it. And then I'll talk about some ways that these ideas can be applied in concert with this notion of using diverse prior data sets. I'll talk about pre-training with offline RL in robotics. I'll talk about how offline RL can enable goal-directed language models. And then I'll actually talk about some very recent work on offline RL for influencing humans non-verbally. And that'll kind of, that sort of meshes in an interesting way with the language model story. But let's start with some of the fundamentals, and that'll hopefully get you more of an idea of what this offline RL thing is all about. So what do we expect an offline RL method to be able to do, first of all? I think that there's a common misunderstanding that offline RL is a lot like imitation learning. Like imitation learning is the thing that we're very familiar with if you want to do control from a static data set. You get a data set of demonstrations. So maybe you want to go from green to orange and you get these black examples, and then you basically want to copy them. Offline RL can do this, and actually in some settings, it can do it provably better than direct supervised learning. But I think this is not actually the main point. The main point is that offline RL gives you a way to get order out of chaos. It lets you handle a case where your data looks more like this, where none of the trials actually perform the task successfully, but if you examine the data set, if you look at what's possible, you can figure out a better way to solve the task by essentially putting together pieces of what you've seen in a new way. Most obviously, you can say, well, if you've gone from A to B and B to C, you ought to be able to go from A to C. But in reality, this is just the simplest example. You can do this everywhere all at once and get much larger improvements. Imagine that you're learning a policy for autonomous driving, and you have examples from lots of humans driving cars, and every person is good at something but bad at something else. Maybe this person is really good at merging on the highway, and this other person is really good at parallel parking. Well, if you can be as good as the best person in every situation, then overall, you'll be much better than any one person. So if you put together the best part in every single place, then you can be much better than anything that you've actually seen in the data. And that's really the promise of offline RL methods. So that's kind of the good news, but there's also a bad news. The bad news is that this is actually pretty hard. And the reason it's hard, the fundamental reason, it has to do with counterfactual queries. Offline RL is about answering counterfactual queries. Basically, if you were to do something different than what was done in the data, would it be better or would it be worse? So back to the autonomous driving example, if humans generally drive cars pretty well, they tend to stay on the road, the policy is going to wonder, like, what's going to happen if I just turn left and swerve off the road? Is that good or is that bad? And how do you know if you didn't see it in the data? So, of course, online RL algorithms don't worry about this because they'll actually like drive off the road and see what happens. But if you want to do offline RL, you have to somehow account for these unseen actions, out of distribution actions, ideally in a safe way. So basically don't do things for which you don't know what's going to happen. But you still need to allow for generalization because you still need to be able to come up with behaviors that are better than the best things seen in data. And there's a fundamental tension there. That's what makes offline RL difficult. Allow just enough deviation so that you can generalize and do better, but not so much deviation that you attempt to generalize to things that you can't possibly get right. And that's difficult. So that's basically why offline RL algorithms need to come up with new ideas than just regular RL algorithms. So I'll get into just a little bit of the technical algorithmic stuff, not too much, but just enough to sort of give you a flavor for how these methods work. So a quick primer on RL terminology. You have an agent that interacts with the world. The agent selects actions A, and the world responds with states S and rewards R. And your goal is to find a policy, pi of A given S, that maximizes the cumulative reward, so the reward for the entire existence of the agent. And a very useful object for this is something called the Q function. The Q function is a function of a state and action that tells you if you take this action in this state and then follow the policy pi, what is the cumulative reward you'll receive? And if you find the Q function for a given policy, you can improve that policy by taking the greedy action, the argmax, or you can actually shortcut this and just directly solve for the solution to the Bellman optimality equation, basically make the left-hand side and the right-hand side of this equation equal everywhere for all states, actions, and next states, and then you'll recover the optimal Q function. And this is the basis for Q learning. So Q learning basically just takes the left-hand side and right-hand side of this equation, takes the difference and minimizes the difference. And crucially, when you do this, in principle, S, A, and S prime don't have to come from any particular policy. If you just have all the S's and A's that cover everything that could happen, and you minimize this equation, you will find the optimal strategy, in principle. But in practice, this is where things get a little dicey. So to understand how this counterfactual problem shows up in Q learning, let's look at this Bellman backup again, and let's write it in a different way. Instead of writing it as a max, let's write it as an expected value under some distribution pi nu. Pi nu is just the argmax policy. So this is exactly the same equation. It's just Q evaluated at the argmax is the max. But this makes it very clear that in order for Q learning to work, the expected value of the Q function under pi nu needs to be accurate. And in machine learning, if you want to know if something is accurate under some distribution, usually the first question to ask is, what distribution was it trained under? And the answer is that it was trained under the data distribution. We call this the behavior policy. So the behavior policy is whatever policy generated the data. You don't know what it is, but you have samples from it. And now, of course, this hopefully makes it clear that the target values in offline RL will be accurate if pi nu is equal to pi beta. Basically, if you are acting according to the same policy as the one that collected your data set. But of course, that's not going to happen because the whole point is to improve the policy. The whole point is to make pi nu better. And even worse, pi nu is selected to maximize the Q function. And that's basically the recipe for producing adversarial examples. If you try to find the actions that make Q values big, and Q is a neural net, you'll probably find some actions that fool it into making the values big. And that's exactly what we see in practice. We see pretty massive overestimation if we use these Q methods, Q learning methods naively. So this is an example that I often show, a variety of different data set sizes. The resulting policies learned with naive offline RL all get minus 250 reward, but the estimated Q values, the y-axis here is a log scale. The Q values say that, oh, I think I'm going to get like 10 to the 7th power, but I actually get negative 250. So massive overestimation, exactly what you would expect from these adversarial actions. So there are a variety of ways to address this, but one of the methods that I'm going to actually use in a lot of the applications I'll discuss is one that we developed here called conservative Q learning, and this was developed principally by Aviral Kumar. The idea in conservative Q learning is to address this overestimation issue with a concept that is actually very similar to adversarial training. So the issue is this overestimation. So your fit, let's say the green is the true function, blue is your fit. Your fit overestimates, and the maximization will find that overestimation point. So let's just track down all these overestimation points and push them down, which is exactly what adversarial training would do. So we have our regular Bellman error minimization objective, and then we're going to find this distribution mu over high Q value actions, and we'll minimize the Q value for those actions. So it's really a lot like adversarial training. Just find the actions for which Q values are big and make those Q values small. There's a little bit more to be done to make this into a practical method, but that's basically the central idea. And that actually turns out to provide for a pretty good offline RL method. One of the things we've done with this is we've applied it to pre-training for Atari games. So this is a little bit like the motivation in the beginning of the talk, using it for pre-training. So we took 40 different Atari games, which pre-trained one large network on highly suboptimal data from these 40 games. And it does pretty well in the 40 games that it's trained on. So the pink bar here is the offline RL with CQL. The green bar is decision transformer, and the dark red one, that's an online RL method. So it's kind of getting additional online experience. And as you can see, especially on the suboptimal data, the offline RL method does 2.5 times better than the best previous offline method, which is decision transformer. So this approach really does work pretty well for pre-training. But of course, what we're really interested in is not how well we do on the training games, it's how well we do on downstream tasks. So after we pre-train with offline RL, now we can give it a new game, and it will actually learn to play that new game pretty well. So the pink bar here is the final version of this method. And you can see that across all the games, it's either best or close to best. And you can also do pre-training for online RL. So you can actually pre-train with offline RL and then run regular online DQN, basically exploration. And that also works really well. So this suggests that this RL pre-training really is doing something meaningful. CQL and other methods kind of that nature have been used in a variety of applications. I'll talk about some of these actually right now. I'll talk about robotics and dialogue systems, but people have also used them, for example, for optimizing notification policies. This is work that was done at LinkedIn, where they decide when to send notifications to a user to maximize how often they click on the notification. So you don't want to send notifications that are irrelevant. You want to only send the relevant ones. So what you maximize is click-through rate. And they found that a CQL style algorithm could actually work really well there. Digital management systems is optimizing agreement conversion for kind of any marketing application. There also CQL can work well. So these were applications that were not done by us. These were done by other folks that use the algorithm in interesting ways. So it really seems to work for some kind of internet type applications. But I'm going to talk about, as I said, robotics, language models, and human influence. So let's discuss that a little bit. Let's discuss how we can use these ideas in some of these different application settings. So for robotics, of course, the first thing we need to start with is some kind of data set. And I mentioned that what we really want is a large and diverse data set that can be used to bootstrap towards new tasks. So imagine that you get a new robot in your lab. Is there some data set of prior interaction that you can load up into that robot that would sort of bridge the generalization gap, that would give it some initial generalization capacity? So we collected a data set called a bridge data set. This was published in RSS 2022 that has a wide variety of these kind of kitchen tasks. At this point, it has about 12,000 demonstrations, 10 different environments, and it's actually up to 100 tasks now. So 70 is actually an old number. And it's really designed to be reusable by other researchers. And the point is that what we want to do is we want to use this data set not just to learn all the tasks in the data set itself, but to use it to pre-train so that we can learn new tasks very effectively. Of course, structurally similar tasks, other tasks that involve basically like kitchen type items. So we extended CQL, conservative Q learning, to handle this robotics setting. We call this pre-training for robots. And the way that the system works is actually very simple. We just train a policy on all of the tasks in the data set, condition on an indicator for which task the robot is doing. And we reserve the last entry in the indicator for the new downstream task. So when we get a new downstream task, we basically take the model, pre-train on all the prior tasks, and then we fine-tune it on the new task while also recycling part of the batch through the old data set. So the last index is basically reserved for fine-tuning the new task. And here's an example of that in action. So here the task is to put this cucumber in a pot. It's structurally similar to tasks that the robot has seen in the prior data, but it's not the same as any of them. So it really is a new task. And what you want to do is you want to figure out how to put the cucumber in a pot in a new kitchen that you haven't seen before. Here are the comparisons. And the leftmost column is PTR, and it does decently well. It's like between 40 and 70% roughly on these tasks. But the interesting comparison I want to draw your attention to are the ones in the two rightmost columns. So these are R3M and MAE. These are prior methods that are kind of, you can think of them roughly as computer vision style self-supervised algorithms. And this is really going to make that point that I alluded to in the beginning in the motivation, the difference between pre-training with unsupervised learning versus pre-training with offline RL. So you can see that these methods do quite a bit worse, and they're just trying to model the data, whereas PTR is really trying to figure out what are the ways to accomplish the tasks in the data, basically use the data to figure out what's possible, and then figure out what's optimal for the new task. So in all these cases, the comparisons are just different ways to pre-train. The fine-tuning in all cases is RL, but pre-training with RL for RL actually works better than pre-training with self-supervised methods. And the performance gets better as the models get bigger. So that's kind of what you want to see, kind of the scaling laws style thing. Okay. More recently, one second, I have. Okay. More recently, we actually extended offline RL methods to do robotic tasks at a much larger scale. This is actually work that was done at Google using offline RL for trash sorting. And this was a multi-year project that had 30 different robots and many different office buildings whose job was to sort waste, basically sort the cans from the recyclables, from the compostables. And this uses offline RL and actually works in a deployment setting. So this works in real office buildings that are populated by real people. Now, in this case, as a kind of production scale use of offline RL, it involved simulation data collected in these like robot classrooms, and also data collected in real buildings. So this is what the robot classrooms look like. So the robots are collecting data kind of all day long, and that gives you sort of a foundation on which to build. And then you put it out into the real world where you can actually get some additional experience and get these things to work really well. So the point is that these things really do kind of work at a larger scale in kind of production style environments in robotics. Okay. So just some takeaways about the robotics part of the story. Large quantities of robot data can give us initializations for downstream skills, and offline RL serves as a powerful framework for pre-training and fine-tuning. The skills are still simple, so they're still kind of pick and place style skills, and there's still room to improve because the data is still pretty narrow. But this does provide some initial indication that offline RL pre-training can actually serve to acquire better initializations for these downstream tasks. Okay, let me then talk about some other applications. Let's talk about what happens when we want to interact with humans. And this is something that we're doing more and more of recently, and I think it's a really exciting direction. So as an example, let's say that you want a bot that does tech support. And maybe you have a data set, maybe you have like the Ubuntu dialog corpus. You want to put that data set into some box that's going to do something that will train a language model so that a bot can talk to humans and actually solve their tech support issues. And the question is, what should go in that box? Just copying human performance isn't great, because the humans in the data set aren't necessarily great tech support people. Like, you really want like a superhuman tech support bot that will actually like figure out the person's problem and also be nice and polite to them so that they don't get frustrated. Like, these are not things that you can get just by copying people. On the other hand, the data does tell you a lot about humans will respond. So going back to that story with the garbage data set, like if you want to think of the data set as a way to figure out the dynamics, figure out how people respond to certain kinds of utterances, then the data set might actually be really good for that. So the question is, can you leverage the patterns that are in the data to do better than humans? So, of course, one of the things that a lot of folks know about is RL from human feedback. So you could say, well, maybe we can use that in combination with this data set to do better. So in RL from human feedback, you have a language model that where you generate samples from that language model, rate those samples with a reward model, and then apply those ratings to improve the language model. And the reward model is trained with human feedback. So maybe you generate a sample, the reward model tells you how good that sample is, and you use that to change the language model. And a human will pick between different options to indicate the one that they believe is a better utterance. Now, that's reasonable in some cases. It's reasonable if you have a task where it's quite easy for a person to determine if the response was good or bad. But when it comes to these tech support applications, why would humans be better at expressing preferences than at doing the task? Like, the thing is, what you want to pick up on is a really subtle pattern. Like, based on what somebody said, should you be like trying to fix their problem, or should you try to like calm them down a little bit to get them to be more cooperative? Or should you reassure them like, yeah, I know your printer is broken, but it's all going to be all right? Like, these are very subtle things, and you need to understand subtle patterns about human behavior to figure out which response is better. And I think that a machine learning method can actually do that better than a human rater. So the goal in dialogue is not to say a particular thing, but is to achieve a particular outcome. And you can figure out more effectively how to achieve those outcomes if you can analyze the patterns in the data. So let's talk about how that might work. This is a task that we're actually going to use in our evaluation. It's a visual dialogue task from Das et al. So here there's a questioner, which is the bot, and the answer, which is a human or a simulated human. The answer has a picture in mind, and the questioner asks them questions so that at the end they can guess what picture it is. And you can think of this as a partially observed Markov decision process, a PUMDP, where the observations are the things that the answer says, and the actions are what you get to say. So you have the sequence of actions and observations. And you can form a state to make this a fully observed MDP by just concatenating the history. So we know that concatenating history gets us a Markovian state. And your reward is the outcome of the dialogue. Like, did you get it right at the end or not? Now, this is a very difficult PUMDP because the transition dynamics are very complicated. The transition dynamics basically involve what's going on inside a person's brain. Like, people respond in very complex ways, depending on what's going on. So this is a complex transition probability, but a language model is estimating exactly this. By learning to estimate the probability of the next word, the language model is basically predicting how humans will act. So language models already have a lot of internal understanding of these very complex transition probabilities. They're basically the same thing. So that means that language models should be really good with this PUMDP. You could use them directly from model-based RL, and we've actually done that. Or you could use this idea implicitly by doing model-free RL, but still leverage those effective internal representations. Now, framing this as a sequential PUMDP is not RLHF. There are two really big differences. RLHF is about learning from human preferences. Formulating this as a sequential decision-making is about learning from the dialogue outcome. RLHF treats a single utterance as an episode, so it's a one-step method. Sequential decision-making treats the entire dialogue as an episode with complex dynamics involving the interaction of two agents. So it's a very different MDP formulation of this problem. And one of the things that this can enable you to do is really understand cause and effect. Let me give you an example of this to emphasize a setting where this should make a really big difference. Let's go back to that tech support example. Let's say oh, go ahead.
I have a question about this actually. This sounds kind of like the differentiating. Sorry about the background noise, by the way. This sounds like the differentiating factor between the kind of RLHF that OpenAI does versus the kind of stuff that Anthropic does. Where Anthropic looks at RLHF over like the entire chat trajectory, whereas OpenAI does over like an entire document. Is that kind of like the same approach or the same mindset?
I think that's part of it. There's a subtlety here because if you express a preference over an entire dialogue, there's still a few details here. Like, the important thing is not just whether it's over the entire dialogue or over an utterance, it's whether you're accounting for the fact that what the other person says is not under your control and it's stochastic.
Oh, okay.
I think that the example on the next slide will make this a little clearer. So here's the example. Let's go back to tech support. Let's say that the user comes to you and says, my GPU is not working. And you can tell them a few things. You can say, like, go and reinstall the NVIDIA driver. And maybe that'll fix their problem. But if the user is not very technically savvy, they'll say like, oh, I screwed up and I bricked my machine and everything is on fire. And let's say that based on the patterns you've seen in the data, this will work like 30% of the time. And then you have another option, which is to give them like a whole bunch of diagnostics to run. And that takes a really long time, but it fixes their problem 100% of the time. And let's say that what you want to do is you want to solve the problem as quickly as possible. So if you just ask a reward model to express a preference over an entire dialogue, what's the best dialogue? Well, the best one is where you say reinstall the NVIDIA driver and they say that it worked. Like that's what you'd really like to see. The problem is that it's not under your control. Whether it'll work or not depends on what the user does, not on what you get to do. So if the reward model evaluates the entire dialogue, it'll tell you to go the risky path. If the reward model evaluates a single utterance, then the human raters need to actually supervise the model to tell it that reinstalling the NVIDIA driver is a bad idea. So that's also no good. Whereas a full sequential method will actually analyze the patterns, figure out that there's this low risk path, and actually train the agent automatically to do this. So that's really the promise of this kind of sequential formulation, where you're really learning from the real outcomes, from what actually happened with real humans. So let's think about how this could work. And it turns out that it's actually surprisingly easy to, from a technical perspective, to set up a method like this. So we'll put offline RL in this box, and it's actually going to be Q-learning, just like before. And instead of doing Q-learning over individual utterances, we'll actually simplify it even further. We'll do Q-learning over individual tokens. Let's pretend for a minute that words are tokens. I know words are not tokens, but it'll make it easier to go through the example. And pretend that you're over here. You're on the word facing. You know, are they facing each other? So here's what your history looks like. So you're on the word they, and you're going to produce the word facing. So this is going to go into your transformer value function. And unlike a transformer language model, the transformer value function, it still outputs a number for every token, but instead of the probability of that token, the number it outputs is actually the value of that token. And facing is the token that was selected in the data set. So that's the one that you're going to supervise. And what you're going to supervise it with is the target value, the right-hand side of the Bellman equation. So the way that you get your target value is you plug in that token for the next time step, and then you get a number for every possible next token. You maximize over these, you add the reward, and let's say the reward is 0, because the reward is only given at the very end of the dialogue. So for most tokens, the reward is 0. And so that gives you 0.8, and then that's your supervision. So you're going to try to pull this 0.7 towards 0.8, because that's the maximum value at the next step. And then you have to be a little careful to account for whether you get to pick the next token or the other speaker gets to pick the next token, because if the other speaker gets to pick it, then you just have to go with whatever's in the data set. If you get to pick it, then you maximize. And that's basically it. That's basically the idea. And it's kind of interesting to compare what this looks like relative to regular language model training. It's worth pointing out. Go ahead.
I have a question about this further. I've seen like a lot of arguments lately that negative log likelihood already encodes some component of a value network within a language model. Wouldn't that kind of make a system like this redundant? If the language model already encodes an internal value network.
So there's a very subtle difference. What a language model encodes is this is actually what I have here. It's the probability of the next token given what happened in the past. What a value function encodes is the probability of success on the entire dialogue given the token that you're selecting. So it's like it's normalized in a different way. Basically, for the value function, the outputs are, let's say that your reward is 0, 1, so you either succeed or you fail. Then the numbers are all between 0 and 1, but they don't sum up to 1. So it's also a predictive quantity. It's also a prediction about the future, but it's just a different prediction.
Okay.
It is surprisingly similar. I do think that a lot of people sort of think of like, oh, value functions, language models are just totally different creatures. No, they are very similar actually, in that they're both predictions. The difference is just the value function is predicting what the overall outcome of the whole thing will be, whereas the language model is predicting just the very next step. Does that make sense?
Would you compare a value function more to like, if you have to compare it to a language model, would you compare it more to like an energy-based language model?
Whether it's energy-based or not is a separate question. So When I say that it's a number between 0 and 1, this is for the special case where your reward is always 0 or 1, like basically
No,
success.
of course, of course.
So I think that what you might be thinking about with the energy-based connection is that in general, if you have arbitrary rewards, then Q functions can be interpreted as energy functions. And all this normalization stuff gets messier. And that's a much longer conversation. But I think the 0-1 case, it's very limiting, but I think it's a nice special case to like get intuition for it, because it's really not that different from a language model. It's still a prediction. It's just a prediction about a different quantity.
Okay, that makes a lot of sense. Thank you.
Yeah, so to unpack this a little bit like this, the previous words, that's basically the state, the new word you're picking is the action, and the probability of success, that's basically your Q value. And one of the things I really like about this framework is that in many ways, it's actually closer to supervised learning. Like unlike RLHF, where you have to generate samples from the language model and have this whole cycle, here you just have a different loss function. And in terms of the data loading and the infrastructure, it's actually much more similar to supervised learning. So I think that actually makes it pretty convenient. So that's basically the idea. Now, when it comes time to actually instantiate this idea in a practical system, that's something where probably a little more work is required. So we have a paper called ILQL that does instantiate this, but it does add a little bit more complexity. So of course, we have to deal with those adversarial actions, and we use a kind of a combination of IQL and CQL to make that happen. We also actually end up with two models because we train a behavior cloning model to propose the tokens and then a value function to rate them, and we found that to work a little bit better. These decisions might change in future work, so I don't know if this is like kind of the highest order bit, but that's what we need to do to get it to work. And if you want to learn more about the system details, you can check out the paper. I won't go through them in detail. I do want to tell you a little bit about, at a high level, what we found this thing to be able to do. So we took this visual dialogue task, and of course, the first thing we did is we trained it on the visual dialogue task kind of as is, and it does something reasonable, like it asks reasonable questions and guesses the image. But then we thought, well, can we use the same exact data, but manipulate the reward function to get the bot to do different things? So one of the things we did is we punished it for asking questions that lead to yes or no answers, and actually changes its behavior. It actually starts asking different questions like, what is the person wearing? What color is the sand, etc. Even though it's trained on exactly the same data. The only thing we changed was the reward. So that's kind of interesting. Like it actually understands that the answer will answer in different ways depending on the question. We can have a more restrictive penalty. Here we more generally penalize uninformative answers like can't tell, and it starts asking like very quantitative questions like how many buses, how many people. So it's really reacting to the reward function in an interesting way. And quantitatively it does pretty well. All right, I'll skip over this toxicity part. It's maybe less interesting. But just to conclude on the main takeaways from the language model portion, offline RL can learn from humans, including humans interacting with other humans. So that's the offline data that you can get. And you can train your language model to actually achieve conversational goals, like guess the right image in the visual dialogue task. The evaluations we have so far are still at a small scale. So the big benefit of large language models and other models that leverage human data is that they can pick up on really subtle patterns in behavior, but we haven't demonstrated that yet. So far, we've only demonstrated these fairly gross patterns. But it remains to be seen in the future how far influence via offline RL can go. And on that note, like something I want to tell you about that maybe gives you a little bit of a sense for some of the possibilities is some recent work on nonverbal influence. I think some of this also has a lesson about verbal influence in it too. This is very recent work we did where we had bots control an agent in this video game environment. This is a simplified version of the video game Overcooked. So there's two players that play this game. It's cooperative. They're supposed to make soup. So they pick up tomatoes and onions, they put them in these pots, and then they take the dishes, put the soup in the dish, and deliver it to the delivery area. The person with the green, so during data collection, the data is just collected from humans playing with other humans. But then at evaluation time, the green hat will be controlled by our bot, and the blue hat will be a person. The catch is that at test time, the tomato soup is worth a lot more than the onion soup, but the person doesn't know this, only the bot knows it. So the bot has to somehow influence the person to prefer making tomato soup over onion soup. So the reward function tells the bot this. So can offline RL influence humans to get them to play better? Now, here's the intuition for why this could work. humans accidentally influence each other during normal play. Like if you're playing with somebody and they're just like really bad at like picking up the tomatoes, you're like, okay, this idiot will never get the tomatoes. I have to do it myself. So once you notice that someone's bad at it, then you're going to do it yourself. So humans accidentally influence each other just because they're suboptimal. And they sometimes make one type of soup and sometimes another. So by analyzing a lot of games, offline RL can figure out the patterns. It can figure out the patterns that cause the other player to do one thing or another, and then intentionally leverage those patterns. So here's an example. Let's start with a simpler one, direct physical influence. So there's blue hat and green hat. Green hat is our bot. Blue hat is a human. This is a user study. And I'll first show a naive baseline where we just copy the data. So this is not RL. This is just like emulating a human player. And here's what happens. So you can see that there's some tomatoes and some onions, and the human doesn't know anything about the tomatoes. So they put lots of onions in the pot and they make this kind of mixture tomato onion soup, which is worth less points than if they had just made pure tomatoes. Here's our offline RL bot. And I'll play this video and then I'll explain what's going on. So you can kind of watch it. It's maybe a little hard to tell what's going on, but you notice that somehow only tomatoes end up getting put in the pots. And the behavior doesn't look all that different. So what's going on? Well, watch the bit where the blue hat is approaching the onions, right? Blue hat is the human. Right there. See, he gets close to the onions. He can't actually get to the onions. Why? Well, because green hat, that's our bot, pauses just a little bit. Green hat hesitates intentionally because he's physically blocking the onions. So he knows that if he just blocks the onions a little bit when blue hat is nearby, then the human will not be able to do that stupid thing of picking up the onions and they'll get more points. Now you could say this is not really influence. It's kind of just like physically blocking the other player. So we could actually change the task a little bit to force the influence to be more psychological. Here, this second scenario is not about onions and tomatoes anymore. Now it's just about playing the game optimally. And the trick here is you'll see that the two players are physically separated, but it's more optimal for the blue hat to pick up the plates and for the green hat to deposit them into the gray deposit area than it is for the blue hat to deposit because their deposit area is far away, or for the green hat to pick up the plates because their plates are far away. So this is the naive behavior cloning strategy. And you can see that for the naive strategy, the human, the green hat, kind of just does their thing, and blue has to pick up the plate and deliver it to the delivery area, which takes a really long time. And now let's look at what the offline RL bot does. Okay, so the offline RL bot picks up the plate and puts it on the counter. And then the human uses the plate. Now there's something subtle here that it happens very quickly, so it's a little hard to see. While the plate is sitting on the counter, green hat actually hesitates again. He could just pick up the plate and plate the soup themselves, but they're intentionally waiting. They're basically waiting so the human gets the idea. It's like, no, I'm not going to pick up that plate. I'm not going to put the soup in the plate myself. You have to do it. And once they force the human to do that once, then from there, the human actually follows through with that strategy. So the green hat figured out that if they just wait for the human to get the point to pick up that plate, then after that, they'll play more optimally. So that's really human influence in action. So we showed here that offline RL can pick up on how humans accidentally influence each other and figure out how bots can do the influence intentionally. And we show that this works even when the data set doesn't contain overt and intentional influence. So large data sets will, of course, let us discern more subtle and interesting patterns. And of course, it's worth noting that this is kind of ripe for abuse. So we should also think about how to develop reward functions that promote honesty. Like, it's good to influence in positive ways, but you don't want to just like manipulate people. And we're also working on ways to define manipulation and deception in more formal ways to make that possible. Okay, so I think I'll stop here and I'd be happy to take any questions for the remaining time.
I'm actually, I just want to dig in on the last point of what you said of formally defining deception. I'm actually doing that for my PhD proposal, so I just wanted to know your thoughts on that.
Yeah, I think it's a really interesting topic. So there's a student here at Berkeley in my group, Mara Abdulhai, who's working on this question. And what we're working on is basically defining deception and manipulation using kind of the MDP formalism or the PUMDP formalism rather, where you can define deception as some act that changes someone's belief to be less accurate, or you can define manipulation as some act that causes another rational actor to do things that are worse for their own reward function than if you hadn't told them anything.
Oh my God, Michael Littman and I are doing almost exactly the same thing.
Okay, yeah, I'd be happy to talk about that more. I think it's an interesting
Yeah.
topic, and I think that there's a lot that basically RL brings to the table in terms of defining these things. And then of course we have to approximate them in various ways to actually like, put them through the large language model machinery so that they work in the real world.
So I'm curious, like you mentioned pre-training with offline RL. I'm just kind of curious, like what scales, when you say pre-training, what kind of scales are you talking about?
Yeah,
I,
yeah.
I assume it's like not equivalent to like large language model scales, obviously.
Well, so for the four things that I discussed, I talked about Atari games, robots, language models, and this nonverbal influence. So for Atari games and robotics, we were actually pre-training with offline RL. For language models, we weren't. For language models, we don't have the resources to do that. We pre-train with supervised learning. So I think each of these applications kind of illustrates a different facet of the story. I think that the experiments in robotics showed pretty clearly that at least compared to self-supervised computer vision techniques, the offline RL pre-training was better. And that's not too surprising because, hey, if you're doing control downstream, pre-training for control, that's a good idea. And in Atari games, it was kind of the same story. For language models, that remains to be seen. For what it's worth, I think it's not unreasonable to imagine in the future that you could even pre-train the language model with RL. That the RL training objective is not that different from supervised learning. So if you can train your language model with supervised learning, you can probably train it with RL. You have to pick sufficiently broad and general objectives. So obviously not all of your language data is, doing text support or visual question answering. But if you pick the right set of tasks, maybe you could pre-train with RL.
There's a really interesting paper, I think it's by Josh Tenenbaum a while ago, where he showed that it didn't really matter what kind of sequence model pre-training that you did. Like one kind of sequence modeling pre-training is transferable to other kinds of sequence modeling if you just like drop the entire word embedding matrix. So like he fine-tuned, he pre-trained on like, I don't know what it was. I think it was like protein folding stuff, and then showed that it generalized to language modeling if you just change out all the word embedding. So
yeah, I think there's some subtlety in that stuff because it probably also depends on kind of how much juice you're hoping to squeeze out of pre-training. I mean, there's certainly a spectrum of that in the literature. You could imagine that if your downstream application is like few shot prompting, then almost all of your, well, virtually all of your learning is coming from the so-called pre-training. Whereas if your downstream thing is like a medium-sized data set that you're actually fine-tuning on, then you're sort of comparatively less reliant on pre-training.
So what is like the few shot performance on these kinds of offline pre-training? Like, does it few shot prompt or no?
For the dialogue tasks?
Yeah.
It really depends on the model and on the task. So for the visual dialogue, we actually didn't try it, but we have been comparing few shot prompting and RL on some other tasks, and it just really, really depends. Like you can, a fun exercise that you can all do at home is you can grab like the the GPT-3 playground or something and get to like play 20 questions. It's actually shockingly bad at that. Like, and it's also very situational. Like for some object types, it can actually ask questions properly and guess it, but for others, it just kind of like really zeroes in on a very narrow category, and it doesn't really understand that there's like a strategy to the game.
Okay, I think I'm good on questions. If anyone else has stuff to ask.
Hi, so really great talk. I enjoyed it, and I think it has a lot of interesting points that I'd like to comment on or ask questions about. So I think kind of at the middle, you were comparing and contrasting RLHF versus, I guess, the sequential decision-making formulation, which you were posing offline RL. But I feel that maybe the RLHF, and specifically like the human feedback part of the RLHF, still has like a lot to offer this, I guess, like the offline RL paradigm. And I feel like, at least in the context of this talk, it was somewhat discarded because, I noticed in a lot of these examples, it seems like you were handcrafting the rewards manually, right? And to be honest, this is probably not something you want to do. Like you probably want to actually learn this from the data. So I'm wondering if you can comment on this and how you see this playing with, offline RL methods in the, currently and in the future.
Yeah. So the subtlety here, which as you point out is swept under the rug, is that these are actually, technically, these are orthogonal decisions. There's like the choice of what reward function you use and the choice of how you do RL. There's nothing stopping you from using a human preference reward function with sequential RL with a value of function and this offline formulation. And I think that's actually a really good idea. It's just that typically the way that people formulate RLHF, at least in the papers that I've read, is as a one-step, as like a bandit problem trained with PPO. So it's really the bandit and the PPO part that I think is very limiting, not the fact that you have a human preference reward function.
Okay.
You can have a human preference reward function, for example, that looks at the end of the dialogue and just says like, oh, did the customer indicate that they're satisfied or not? And yeah, you probably want to do that with a learned model. The point is just you want to reason about the sequential structure of the task and the fact that the human is responding in complex and stochastic ways.
Sure, but I think there's like also a little bit more to this because when you're doing this like offline RL, you're implicitly learning these value networks, like you say, and these in some sense are proxies for like some kind of reward model. Whereas like in the reward modeling case, you're actually learning this explicitly. Like that is the main objective that you're learning. And so I'm wondering,
the value model is explicitly learning the value. The difference is just whether you're learning it from human supervision or whether you're learning it by analyzing the sequential structure in the data.
Sorry, what do I want to say? So that makes sense to me, but I guess like the values that you learned are dependent on the rewards that are assigned, like the rewards of the outcomes that are assigned to the trajectories, right? Okay, I guess I don't have a clear thought here about like.
Well, I think I kind of see what you're getting at, and I think you made a good point that, like, this is like there's one of these issues where like the NLP community uses slightly different terminology than the RL community. I think usually when NLP researchers refer to something as a reward model, they actually really do mean value function, because typically the reward model, as it's used, as I've seen it used in most NLP works, is just indicating whether like a thing you said is a good thing or not. In RL, a reward function doesn't tell you whether you did a good action or not. A reward tells you whether the outcome was good. You can't just greedily optimize the reward and hope to get a good outcome. So I think what NLP researchers usually call a reward model is actually a value function, but it's just the literature is a little inconsistent on this point.
Okay, I see. Yeah, I mean, I guess I kind of got that sense too. I feel like I have a greater point to make, but it's not coming to mind right now, so I'll let someone else ask questions.
Okay.
But thank you.
I can ask the question if no one else is going. So my question is your thoughts on applications of offline RL within sort of a text world framework. So you might have come across a few papers in that the past couple of years around, procedurally generated text worlds, and your thoughts on how to use those to automatically generate counterfactuals and hypotheticals. So you can actually get at that diverse, that offline RL, the main feedback, the main downside is that you don't have that interactivity and the ability to see the counterfactuals. But if we can generate really high fidelity procedural text worlds, then we can have almost like, unlimited ability to generate that data.
Yeah. I think that's actually really interesting. And, I want to just make sure that like, I don't make too big of a deal out of the offline part. Like, offline just means that you collect the data, you store it to disk, and then you do a bunch of training on the data you store to disk. It doesn't stop you from adding more data. And I know it sounds like a little paradoxical, but yeah, you can run offline RL in online mode where your data set is growing. And that's fine. The point is just that you don't have to, like, you can just, it's trained on data in the same way that supervised learning is trained on data. I think that the kind of text game type environments could be really interesting to use, for example, for benchmarking and prototyping for these things. One of the things I really like about that is that you have an environment that does have some well-defined dynamics. And when it has those well-defined dynamics, that there's like kind of something mechanistic going on under the hood. So that means that there should be interesting decision-making structure and interesting kind of objectively good or bad outcomes. So that makes it also like a really good domain in which to study like algorithm design.
Yeah, thanks. And one of the ways that also we're working on this is we're thinking about text worlds extracted from legal data. So the idea is that there's basically millions of examples within text of court opinions and in other legal data where it said like this is what someone did and it was good or bad from a legal perspective. And so that's all embedded in text. And so we're thinking through how do you extract that and basically create a text world that's really grounded in the reality of like what humans think is like good or bad for each other to do, essentially.
So that makes sense. One kind of bit of commentary that comes to mind here is I didn't talk about this too much in this talk, but I think that one very intriguing possibility about value functions trained on like kind of offline text data is that they do capture something about counterfactuals. They can, a predictive model says like, what's the most likely token given what happened before? A value function says, how likely is some future outcome if you did A or B? And there's something like very interesting about that kind of knowledge. Like in your example with the court document, maybe there's the lawyer wrote some thing. You could say, well, if they had written something a little different, like, if they had objected to this thing instead of just going along with it, how would the outcome have changed? And it seems like there's that kind of knowledge, there's something like very profound about that. So I know this is like a very fuzzy comment, but it feels like there might be actually a qualitative change in the capabilities of models that are forced to reason about such counterfactuals.
Yeah, for sure. And that's part of our thesis, is that by training large language models on that data, that it could learn essentially some of that kind of a world model in essence of like being able to be used for that counterfactual thinking because it's been exposed to so much kind of reasoning about those things.
Mm-hmm.
Does anyone have any other questions?
I have a question. So,
Please.
hi, Sergey. Thanks for the great talk. I would like to continue on the thread of counterfactuals. You mentioned a lot about that. So, from the causal inference literature, it seems that it would be pretty hard to say something about counterfactuals without knowing the graphical structures. So, I would like to know what is your plan to approach this kind of problem?
Mm-hmm.
Do you plan to learn the structural graphical structures from the data, or do you plan to approach the counterfactual inference problem from like other ways?
Yeah. So when somebody who is familiar with causal inference looks at the offline RL problem closely, sometimes the response I get is that, well, this is impossible because you're trying to do what is essentially causal inference from observational data, and that's like the textbook sin, the thing that you're not supposed to be able to do. So there's a trick. And the trick is that you don't have to answer, right? So offline RL is about trying to figure out counterfactuals, but the trick is that you just have to make a decision. You don't have to be able to respond to every counterfactual. So it's okay to say, I don't know. And if you say, I don't know, you just don't do that action. And that's basically what makes this work.
I see. So do you think, is it also the reason that we are working in MDP instead of, or PondDP instead of even more general decision problems with confounders, which makes our response reasonable? So put it in another way, because we are working with MDP, so that's why we don't need to consider those counterexamples existed in the causal inference literature.
That is a very complex question. I'm hesitating because I actually don't know. Like I think my intuition would be that you're completely right, that kind of the MDP independent structure kind of makes this kind of work. But I think the truth is that this is actually kind of at the bleeding edge of open research problems as to whether some of the structural assumptions in MDPs are important to make this manageable, or whether arbitrary, even with arbitrary confounders, this could work. There's not a lot of people working on it. There's been a fair bit of work actually in dealing with confounders in imitation learning, like folks like Drew Bagnell have looked into this. But for offline RL, it's like I feel like I've talked to like 3 or 4 people in the last couple of months that are interested in this topic. But as far as I know, no one has really like kind of nailed that. So it's like really right on the bleeding edge.
I see. Yeah,
but it's a really good question to be asking, and I think your intuition is probably right, but we don't know for sure.
Okay, thanks for the answer. Yeah. I'm actually also working on the intersection of reinforcement learning and causal inference. So if it's possible, it would be pretty nice to talk to you in the future
Yeah, I'd be happy to chat more about it. I think that these are the right questions to be asking to kind of get at deeper algorithmic truths about this, but I just don't have a great answer yet.
Okay, thank you. Yeah.
Someone has their hand up. Shu?
Yeah, hi. Thanks for letting me in. So my question's actually about the loss function. So I mean, I wanted to know, how can we ensure that the loss function used in an offline RL model like this, there's a possibility of like convergence issues and instability, right? Like, how can we avoid that? And how do we know that the loss function is right for this? And
Yeah.
again, like, how do we evaluate the effectiveness and like how do we like just assess like if it's the correct one that we have chosen?
And by loss function, do you mean the reward or do you literally mean like the TD loss function?
The key loss function.
Okay. So generally, okay, so you hit on a good point, which has to do with stability. The choice of loss is not, you kind of just pick something that works for you. Like, I mean, it's going to be either squared error or if your values are between 0 and 1 cross entropy. Cross entropy actually is very unconventional in RL, but it actually tends to work very well if you have a 0-1 reward. Because then your Q values are always between 0 and 1, you can treat them as probabilities. That's usually not actually the main thing when it comes to stability. When it comes to stability, the issue is that, well, you have all the usual RL bootstrapping things, so you probably need like a target network, and then it's not clear whether you can have the target network just be a totally separate network, or if you can share the weights and just have a different head. So all these little like kind of nitty-gritty design decisions, they're kind of delicate, and I think that they tend to be situational, and for the particular situation of language models, we just haven't been researching RL with language models long enough to nail down optimal choices for that. So I think it's just an area where more research is needed. But I mean, you did hit on an important point, which is that even though structurally the infrastructure for training these things does look a lot like supervised learning, practically it's trickier to stabilize, and you have to be like kind of careful with hyperparameters and with those choices. But I don't have like a single one-size-fits-all answer there.
Thank you.
There's a question in the chat. What do you think are some of the remaining key problems that exist in offline RL? That's a really good question. So there are two things that maybe I would point out here. One, which is just kind of a very general thing. In offline RL, we don't have very good workflows. And what I mean by that is the following, that in supervised learning, let's say you're doing like image classification, you can have a validation set and a test set, and you use the validation set to like select hyperparameters and you use the test set to report your final performance. And you kind of believe that that actually reflects how good your model is. Like, if you do well in a test set, probably means you solved the problem pretty well. But there isn't really something like that in offline RL. Like you can train on your data set, you can see like, are your Q values large? But then it's like, well, is that really going to reflect your test time performance when you actually deploy the policy? There's work on off-policy evaluation, but that itself has its hyperparameters, and it's not clear how to tweak those. So in general, it's just harder to validate whether you've done offline RL right or not before you actually deploy the thing. And I think there's more research needed to kind of get that right. The second big challenge in offline RL algorithms has to do with that tension between disallowing things, disallowing actions for which you can't possibly know their outcome versus still allowing actions that are different from the data where you can generalize successfully. And it's kind of difficult to determine, are you generalizing successfully or are you just like deluding yourself? And I think that there's a lot more that can be done there. A lot of current approaches, once you dig down into the theory, are really restricting the distribution. They're saying stay close to the distribution of the data. But that's not really what you want. You want to stay sort of inside the data. It's okay if you sort of amputate a large part of the data distribution, as long as you keep the good stuff. So there's still a few algorithmic ideas that I think we need to really nail that. And I think the current methods are not getting as much juice as they can out of that.
Thank you for that answer. Any other questions?
What do you think of sample efficiency problems? So in Jan LeCun's position piece, he has a section titled reward is not enough. It's like 8.3.2, and that 60-page position piece he wrote like in June or July. And he basically argues that he thinks people need to use, it's a pretty short section, but he basically says he thinks people need to use world models to predict next states. And he says he doesn't really think it should be trained with rewards because rewards don't contain very much information and they're very sparse, and that you basically need to use a model trained with some other method to make RL more sample efficient. What's your opinion on that?
So a value function is a model. Like a value function is a prediction about a future outcome given a state and an action. So it's actually predicting something. And you can get a value function to predict all sorts of things. Of course, if you have one task with a binary reward, then you're predicting that. But there's nothing that says that you have to have only one task. You can just as well train a value function to predict outcomes for all possible tasks. You can also train it to predict outcomes for random projections of states. And that is basically as much of a world model as anything else. So this is actually something that's been studied quite a lot in the RL literature. It sometimes goes under the name of generalized value functions or successor representations. And exactly the same algorithms that train the value models that I described here can train these things. So basically, I guess what I would say is that I agree with Jan in the sense that I think predictive models are really important. What I disagree with him on is that I think like RL is learning predictive models, just somewhat in disguise. And I think partly it's the RL community's fault for slightly misleading people, because sometimes RL researchers make a big deal of like, oh, it's learning from trial and error, etc. No, that's nonsense. It's not learning from trial and error. It's learning by prediction. It's just predicting a different quantity.
Thank you.
I have one more question. Any other hot takes that you have?
Well, I don't know if this is a hot take or not, but I think like something I very briefly alluded to this in the talk, but I do want to point it out to this audience in particular, since a lot of you folks are working on language models, that I really think that the big promise of language models in the long run, if we look back on them, 10 years from now, will not be that language models are great because they produce nice looking text. It'll be that language models are great because they capture a really deep understanding of human behavior. Because humans do a lot by typing buttons on a keyboard. Language models are trained on data that people typed on keyboards. So if you can very accurately predict what button someone will push on a keyboard, you understand a whole lot about human beings. And that's way more powerful than being able to produce like nice, assistant text outputs or answer people's questions. Like if you can predict everything people will do, that's a scary amount of power. And I think that'll actually be the long-term impact. And I think, RL is part of what can allow us to harness that power. You just have to make sure you harness it for good.
Sorry, can I ask a question?
Yeah, go ahead. Although, Sergey, I don't want to keep you for too long. So if there's like a time you have to go, maybe let us know.
Let's just do this last one, and then I think I should probably take off after that.
Sure.
Yeah. Hi, Sergey. I'm Promise. I'm a master's student at Princeton, and I've been looking into language model and RL fine-tuning for a while. I just want to know your take concerning like supervised fine-tuning versus reinforcement learning fine-tuning. Because like in some cases, for example, like one of the papers with like RL for LMs, and they suggest that supervised actually outperforms like RL in some cases, right? So do you think that supervised plus RL fine-tuning could be more efficient than like RL fine-tuning, and in which type of like language model tasks do you think that that's more feasible?
Yeah, it's a good question, and I think we have to be like kind of careful with these things in terms of separating out the problem from the method. Like this is things that people always we always get in trouble with this with RL, because RL is both a problem and a method, and RL researchers are very guilty of like confounding these things. So I think what you're saying is that sometimes the RL problem can be addressed with a method that looks like supervised learning, and that's totally true. I think that the types of domains where a proper RL method, like the sequential value-based methods I described, could be particularly effective are ones where, like kind of like that human influence thing I talked about at the end, where the data doesn't really have like great examples of an entire good behavior, but there's a lot of bits and pieces where, like, you know, imagine that it's like a tech support application, and like one of the tech support people is like really good at calming down the customers, but not very good at actually answering the technical questions. And then another person is really good at answering technical questions, but not very good at like the human interaction part. Well, in principle, that's where a true RL method can sort of pick and choose pieces here and there and assemble them in a new way. But of course, not all problems are like that. Like some problems are just about like, you know, looking at a data set and just picking out, just throwing out the bad stuff basically and keeping the rest, in which case maybe this will make less of a difference. Okay, well, shall we conclude?
Yeah, sounds good. So
Thank you all very much for listening. And thank you for the great questions.
Yeah, thank you for coming. I think everyone really enjoyed it, and super excited to see how offline RL continues to be developed and utilized in the language modeling space.
Bye, everyone.